Before we do that, I do want to come back to this slide. Okay? I definitely got a few questions about it after the last class. Everything on this slide you should have memorized already. If you do not have it memorized, memorize it now. It is the only way that you can do these problems. Okay? You have to have all of this information quickly and readily available to you. You can either memorize it or memorize it just long enough to write it down directly on the exam before you even put your name on it. It's entirely up to you. Okay? This slide shows up in the slideshows, so it's not like it's a random new one, so you don't have to frantically write it down now. You just need to know what it is. Okay? Oxidation states, I left this one up here just for our definitions on what is oxidation and what is reduction. So you guys should have those memorized already as well. And then as far as this is what I wanted to have up there when you guys went through it, was all the individual steps for balancing. Okay? I broke down the problem that you have in front of you into these steps. It looks like I didn't do a very good job numbering though. So that you would see each of the individual parts so that when you go through and approach it, you go through and do it in the correct order, and it should help and get you to the correct answer. This problem we've got up on the board, so you can see that answer for those of you that are in class. The next problem apparently had an issue with spacing, is the one directly off of your quiz. Okay? So, ta-da, magic of time, there you go, you've all practiced it, good job. So, what are your answers? Yes, question?
Was there a space when you times the two equations right here for the MN? What do you want a 2 here?
Oh yeah, there should be a 2 there. I didn't leave a space there. Yeah, just squeeze it in there. Okay? Did everybody get that answer?
Yes.
Sounds pretty good. Okay? So when you go through and balance, we could go through and show this in the show your work. I personally probably wouldn't put it there because a lot of you are going to skip steps because you'll do enough practice that you'll be able to skip a lot of these steps, which means it's going to be too difficult for me to grade individual steps of your work. Okay? So it'll likely show up in a multiple choice situation. So how do we ask a multiple choice question on this? Okay? So what can we do? I could go through and we got 3 different possibilities. Say provide the sum of the coefficients for the balanced reaction of permanganate and sodium bismuth oxide. Okay? I would also give the products. I just ran out of space in this case. Okay? So what would you have to do? Go back to your balanced equation, add all of the numbers up that are in front. Probably the hardest question I could ask because it requires that you have the entire thing balanced beginning to end. So you would add those all together and hopefully what you get, if I remember right, 40? Anybody check me on that? And you would see that answer show up. Okay, and that would be the answer you would select. Other versions of this. How many electrons are transferred in the redox reaction? So you would have to go back and say, okay, to balance that equation, how many electrons do we need to pass between them? So go back to the half reactions that you've got. Okay, possible answers that you would see, 2, 5, and 10. Which one's the correct answer? 10. 2 and 5 were correct to balance a half reaction, not the entire reaction. To balance the overall reaction, you needed to transfer 10 electrons. So the answer you would have would be 10. Okay? So it's looking at a different step within the balancing process. The last one I didn't even provide multiple choice answers for. How many water molecules are needed to balance the reaction? So you'd go back to your balanced equation. That's one you'd probably have to do the whole process for to find that you needed 7. I could add one more piece of information to that question. I could add how many water molecules were needed to balance and what side of the reaction were they on. So we could see 2 answers. 7 reactants, 7 products. Which one's the right one? I'm not looking at the answer, so I don't know it. 7 products. Okay? So there's a variety of ways that I can still ask multiple choice questions about balancing problems. These are the most common ways that you'll go through and see those. I'm pretty sure all three of these show up on your practice homework. Or sorry, your practice exams. Okay? Any questions about that? Relatively confident, happy with that? Okay, let's make it worse. Okay? In this situation, we balanced with H+. What kind of a solution has hydrogen ions? An acidic solution. So instead of making it acidic, let's change it up. I don't want it to be an acidic solution. I want it to be basic. Okay? How would we balance the reaction in a basic solution? Okay, we would add OH. Problem with adding OH is we bring in both hydrogen and oxygen. It's going to make it odd to go through and balance. So how do we account for this? What we're going to end up doing, wow, lots of steps. We're going to go through and solve the acid problem as if it's an acid. So we'll add H+, water, all that fun stuff. We'll get our acidic environment. And then to make it basic, I need to get rid of the acid. How do we get rid of acid? You add base. So what we'll go through and do is add enough base to both sides of the reaction. Because if we add it to one side, we have to add it to the other to cancel out the H+. What happens when H+ reacts with OH-? Becomes water. Okay? So now when you go through, you'll have your balanced equation with your acid. You add the correct amount of base to both sides of the reaction. The base will react with the H+ on the H+ side of the equation and become water. In theory, we now have water on two sides of the equation. We'll have to go through and account for that, balance those out. Okay, I know I just walked through it without actually showing it. We'll look at it here. Okay? So with this exact problem, we've got our balanced equation. We went all the way through, got our acid solved for. Okay? Now what we want to do is solve for it in basic conditions. We had 14 H+ moles or molecules, however you want to look at it. To get rid of that acid environment, I need to neutralize all of those. So to neutralize 14 moles of H+, what do we need? 14 moles of OH-. So I'm going to add that to my reactant side. At the same time, I'm going to add it to the product side. Okay? What happens? Well, the 14 H+ and OH- becomes 14 moles of H2O. On the product side, is there anything to react with the OH-? Nope, so it stays OH-. So when we add these two up, hopefully I did stepwise this enough. Looks like I did. We would end up with this overall result. We've got 14 water molecules on our reactant side because our OH- reacts with the H+. It doesn't change any of the other species in our reaction. We look to the product side and we just add in our 14 moles of OH-. Okay? We could attempt to stop there, except we can simplify further. And if we can simplify, that's what we should do. So what do we end up doing? We want to cancel the water. To do that, what we can do is subtract 7 moles of H2O from both sides, which I think I've actually got stepwise out here in the next step. Our result would be 7 moles of water on the, did I do that right? Yeah, on the reactant side. See, and there we go. We get our overall equation. Now, is this reaction occurring in an acid or base solution? Base solution, how do you know that? You see the presence of OH-. We're looking now at a basic solution. Okay? So the ways that we could tweak the previous problems that we looked at would say, okay, how many water molecules are required to balance this reaction in basic solution? Okay? We'd end up with, it's still 7, but now our 7 molecules of water are on the reactant side as opposed to the product side. Okay? So be aware of all of these little intricacies when it comes to balancing. Pretty much if you just keep track of everything, your accounting is good. You should be fine as far as balancing goes. Okay? One of the problems that I foresee with balancing questions is that they take a lot of time to go through and process. Okay? So while they may be easy and you may be guaranteed the answer, you kind of got to weigh that against the time investment that you've got to put into it. Okay? Questions about balancing? Because I don't think I talk about it anymore. Okay. I went through, well, I didn't go through and do it. With each of these equations that we've gone through and solved already, you should now be able to convert these all into a basic solution. Go through, attempt those, make sure that you can get them correct, make sure that it makes sense. Okay? Questions about any of that? Okay. So why do we end up caring about any of this? Okay, well, the biggest issue comes with pretty much our everyday lives. Okay, in fact, all of the lights that we see in here, our cell phones, all of that, comes from electrical power. It's the transfer of electrons. So what we want to understand is what's happening in the process of each of these reactions is a motion of electrons. If we can control that flow of electrons, we can power all of our personal devices. Okay? So when we look at an individual battery, that's what's happening. We've got a positive and negative end of our battery. When we connect that circuit, we're looking at the electrons flowing through our device, which then powers our device, flowing to the opposite end of the terminal. We can get some charge, we can get some portable energy. Okay? So it's vastly important to everything that we deal with in modern society. Okay? So what we're really hoping for is this flow of electrons. Okay, so the comparison I'm going to keep coming back to would be kind of an ancient example. We've seen the flow of things before in our past. We looked at the flow of water, okay, rivers. We used that energy, the energy stored as the river or the water runs from the mountains down to the ocean. We can take advantage of that energy by converting it into mechanical energy using a water wheel. Okay, we use it to this day to actually generate electrical energy. Okay? It's using the same idea. We're taking a standard flow and we're diverting it to do something that we want it to do. Okay? So that's going to be the kind of the crux of this chapter, is trying to divert that flow. How can we divert it? Okay, and that's where we end up with batteries. So in this case, what we've done is took zinc metal and dipped it into a copper solution. As we give it time, we notice that that zinc metal starts to get this black crud all over it. And as we give it more time, the blue color, in the solution disappears. Okay, what's happening? Well, we could go back to our equation, and what we see is that the zinc actually starts dissolving. And what's the opposite of that is that we see copper metal start to plate out. Okay, or in this case, if it's black, we're probably seeing a copper oxide. Okay, so why is this happening? Well, it's an electron transfer reaction. We do have a redox reaction. The zinc metal is giving up 2 electrons to our copper ion and forming the copper metal. So we could go through and break it into the half reactions and see that indeed we do have 2 electrons being transferred. And in this process, we aren't controlling that electron transfer. Our goal is to make sure that the electrons move exactly where we want them to, in no other position. So what we end up doing is generating something known as a voltaic cell or a galvanic cell. So instead of putting these things all in one big solution, we separate them. Okay, we separate them and then connect them back up in a very particular fashion. One with an electrical wire, okay, to allow for the flow of electrons. Why a metal wire? Electrons flow naturally through a metal wire because we're looking at an electron cloud or electron, actually I don't know what it's called, some massive electron cloud. Okay, the electrons freely scatter through the metal. It's one of our properties of metals. We'll also have to connect it up with something known as a salt bridge in the middle. We'll discuss that in a little bit. Okay, so we've got this salt bridge connecting them and our metal wire. When we go through and do this, we've diverted the flow of electrons. those electrons now must flow through the wire. That's the only place they're stable. They're not stable in solution, but we can stabilize them within a metal. Okay? So now as the electrons pass through the metal and make it over to our other electrode, we can then monitor that flow of electrons, take advantage of it, make it do something for us. Okay? Much like we would do with the water wheel. Okay? So what we've got here is what's referred to as a voltaic cell, or if you have to take any standardized tests, apparently they like referring to it as a galvanic cell. They're both referring to the same thing. Okay? So now what we should do is try and figure out what happened in the course of this reaction, or identify the individual pieces within this. Our zinc acts as the source of electrons. So if we go back and look at our balanced reactions that are up at the top, so first off, we've got our overall reaction. And then we've got our individual half reactions. And with our half reactions, I know you all love it when I go color coding, so I'm going to go color coding some more. There's our overall with purple. Okay. If we look at our half reactions, our zinc metal gives up 2 electrons to become zinc ion. In that case, what happened to it? 2 electrons were lost from the zinc metal. Our zinc was oxidized. Okay. What happened to the copper ion? Well, if we look at the next reaction, the copper ion gains 2 electrons. What kind of a reaction occurs when we gain electrons? Reduction. Okay. So we could now go through and identify those individual species into our individual compartments and what's happening in each case. Our zinc acts as the source of electrons. Okay. Instead of calling it the oxidized compartment, what we end up referring to it is the anode. Okay, so it's just an extra term that you have to memorize. Okay? The copper lacks electrons, so it starts drawing them towards it, and it becomes the cathode. Okay? So what's happening in the anode compartment? What type of reaction? Oxidation. Wondered where the color coding came from? Blue, right? Reduction, red. Okay. So what we can go through and do is continue to look at this. We can look at our individual reactions, identify each of our pieces. Our anode gave up electrons, so we could go back to our reactions. Which of our half reactions lost electrons? The zinc, which was our oxidized reaction. Our cathode accepted electrons, so what occurred to it? Gained electrons, or it was reduced. Okay? In all of these cases, one of the big issues that we're going to find is that we end up with a non-neutral system, if this is what actually occurs or flows on its own. Okay? We want something neutral. So let's propagate this a little bit further. What happens in each section? So if we take a look at the zinc section, if it continues to lose electrons, what charge does that anode become? If it loses electrons, it becomes positive. It's lost a negative charge. What happens to the cathode? In the process, it's gaining electrons, so it should become negative. Okay? Just like I've crudely described back in politics, we're striving for neutrality. We don't want to build these charges. The more charge we build, the less likely the reaction, or the more quickly the reaction is going to occur in the wrong direction as far as we're concerned. Okay? So what we have to do is come up with some way to neutralize that charge. And so the one thing that we didn't really talk about yet is what's known as the salt bridge. It acts as a porous barrier between the anode and cathode compartments to counteract the flow of electrons. Okay, so the hope is that when we run an individual galvanic cell, that the charge does not build at either end. Our overall charge stays neutral. Okay, how does that work? So if we go through, I don't know why that says end slide. Okay, we just went through and described that our zinc electrode would build some positive charge as it loses electrons. Our cathode is going to build a negative charge as it gains more electrons. To neutralize that, what do we have to do? How do we neutralize a negative? Okay, we could try and remove electrons, but that's doing the opposite of what we want it to do. The only other option is to add positives. Okay? Our standard way to, or what we might consider as far as adding positives, would be adding protons. Protons are even more unstable than electrons, so we need another source of positive charge. Where do we find that? We could go to acid, but we don't have to do that. Why would we not use acid? Looking at a standard battery, it might be nice to not have it be super, super toxic and dangerous. Kind of. Almost all batteries are. Instead of adding a hydrogen ion, we could add OH is negative, but going in the right idea. We could add any other atom that's positive. Okay? Lithium ion, sodium ion. We've got tons of other counter ions that could act as positive charges. Okay? Hydrogen is just reactive as an acid, so we would see side reactions with it being an acid. If we use sodium ion, what do we know about the reactivity of sodium ion? According to our solubility rules, it does nothing. Okay? So it acts as a spectator. So our salt bridge is there to allow for the flow of electrons, or to allow for the flow of ions. Let's see. Yeah, good. Our salt bridge allows for the flow of ions to balance out the electric charge. So if we take a look at our cathode, it accepts electrons. So great, our electrons flow towards the cathode. Okay? To balance out that excess negative charge, we need to balance it with a positive. So what starts to flow through our salt bridge? Positively charged ions. In this case, sodium ion. Yes?
Is that actually how the salt bridge is set up, or is that just a representation?
Depends on the individual situations. A salt bridge can mean all sorts of different things. In this case, it works best because we can see it better. But there is always a salt bridge. It just takes different forms. Okay? What happens on the anode side? We said it builds up a positive charge. To stabilize that positive charge, what does it need? It's going to need some negatively charged species. Okay? If it's electrons, we end up doing the opposite of what we want. So instead of doing electrons, we'll go to a negatively charged ion. What ion is most common? Pseudo hint. The nitrate ion. Why do we typically use sodium and nitrate? Rule 1A was our solubility. Sodium is always soluble. Rule 2A, maybe? It's sulfates? I don't think it's sulfates. I think it's nitrates. Isn't Rule 2A nitrates? Or is that Rule 1B? Nitrates are always soluble, okay, without any exceptions. So when we look at a salt bridge, our most common ions that we'll find within our salt bridge are typically sodium ions or nitrate ions because they're very unreactive. They're very easy to just pass between these. We don't have to stress about other side reactions occurring. Okay? We now have the entire process of our voltaic cell all put together, and we can now generate charge, okay? Or we can generate flow through what's known as a voltmeter. It's how we monitor our electric flow. Okay? One of the things that becomes difficult is we now have a whole bunch of different pieces within this. It can be difficult to memorize and keep them all straight. I know I get them backwards all the time. So there's a couple ways that we could go through and do this. I've been trying to color code, and I think it's consistent throughout all the slides. At the cathode, we're getting reduction. Reduction was a gain of electrons, so we could memorize that with our GER. Our anode had oxidation, which was loss of electrons. There's our Leo statement. How do we tie anode to oxidation, cathode to reduction? We always have to have some fun. We can look at it as a red cat for reduction cathode. And then if anybody recognizes the blue ox, beige blue ox, so anox, anode, oxidation. Okay? Don't shake your head at me. It is Paul Bunyan's ox, yeah. Babe the Blue Ox is Paul Bunyan's, yeah. Okay? Keep all of those individual terms organized and put together. It's very easy to get them swapped, particularly as we run through different reactions. Okay? So at this point, we now know how to set up our voltaic cells. It might be nice to actually run, well, I'm sure you don't want to actually run some calculations, but we want to come up with some ways or other ways to represent these. I'm going to spend a very small amount of time looking at cell diagrams. So we could go through and draw out this giant voltaic cell with all those boxes and cats and all sorts of other fun stuff on it every single time we wanted to look at an individual problem, or we could come up with something a little bit simpler. Okay? So the standard notation when we're looking at cell diagrams, okay, it's not something I don't think I'll directly test you on the exam, but you will see it in your homework. Your anode, by definition, is placed on the left side while you're trying to write these out. The cathode would then be placed on the right side of our diagram. We would use a single vertical line to represent any phase changes. So when we look at the zinc to copper, on the anode side we have our zinc and our zinc ion. So we could write them next to each other, showing the single line between the phase boundary between them. We would then also need to represent our salt bridge. The salt bridge is represented by a double line, separating our left from our right, or our anode from our cathode. Okay? So it's just the standard way that we go through and describe our individual cell diagrams. Okay? So if we go through and take a look at this, okay, I just wanted to make sure. If we go through and look at our cell diagram, we could go through with the reaction we've already established. This would be the cell diagram for our chemistry. Okay? So what we're saying is we're taking zinc metal, and it is converting to zinc ion. Notice that we run left to right. What's the other? Sorry, that should have been blue, right? Sorry. If I say I'm going to stick with color coding, I should stick with it, right? So we read our left to right direction. We're going from zinc to zinc ion. If we look at what's happening in our cathode compartment, we're going from copper ion to copper metal. You'll notice it runs left to right all the way through it. So we try and set up a formatting that allows us to be consistent so that when we see this notation, we know exactly what they're referring to and how each piece is coming together. Okay? You can get these to be relatively complex when you add in all sorts of other things or other phases to these. Okay? I think your textbook discusses some of them in the text itself. I won't directly test you on any of the more complicated ones. I don't even think I assigned any homework on it. Okay? Questions about cell diagrams? Okay. So the next part is, why does this chemistry work? Okay, which is going to start to bring us back into thermodynamics. So if we take a look at putting zinc metal into a copper ion solution, we do see a reaction. Okay? The copper does precipitate out of solution, and our zinc ion or our zinc metal dissolves away. We do see that. It happens spontaneously. If we try the reverse, we take copper metal and we drop it into a zinc solution. Nothing happens. Okay? Why does one work and not the other? It's not electronegativity rules. What we're going to start to look at is cell potentials. You can probably tie it back to electronegativity if you want to get more advanced with it, but we're not going to do that. Okay? So what we could do is go back to 151. You guys remember your activity series? Okay? We could look at an activity series for this. Okay? And if we went back and looked at this, let's see, can I have my circles on here? We could identify our zinc and our copper. The activity series represented what? So if we took it lithium versus gold, what are we saying? Let's go to lithium versus gold first. Decreasing activity. What's the activity we're referring to? its desire to become an ion. So if we look at gold, the bottom of our activity series does not want to become an ion. Does that make sense? What's most of our jewelry made out of? What do we put all of our value as far as our society into? Gold. Why? It doesn't change its physical state. Okay? Very difficult to get gold to react. Okay? Which means we can store it for centuries and not have to worry about its mass changing or losing value. Well, losing the value that we put into it. Okay? So it's one of our common reasons behind gold. If we take a look at lithium, okay, what's the issue with lithium? Highly reactive. What is it highly reacting to become? Lithium ion. It's desperate to get rid of those electrons because it wants to satisfy its electron configuration, become more stable. Okay? So when we go through and evaluate these now with zinc versus copper, zinc is higher on the activity series, which means zinc wants to react and become an ion. So when we go through and look at our reaction, case 1, zinc metal wants to become zinc ion. To do that, something else must accept those electrons. So we can take a look at copper. Copper metal does not want to be an ion. So we go back to our reaction. If we take a look at reaction 1, zinc goes to zinc ion. That's a good thing. It wants to become the ion. Copper ion going to copper. Does copper want to do, or sorry, let's switch down to these two equations. Zinc definitely wants to go to zinc ion because it's relatively high. Does copper want to go to copper ion? No. We can take that information and go back to our equations. In our very first one, zinc going to copper ion is a favorable reaction. It's coupled with copper ion going to copper metal, which according to our equation makes sense. We want to be the copper metal. Okay, lower activity. If we go through and look at equation 2, copper going to copper ion, does it want to do that? Not in comparison to the zinc. Which means what occurs? Case number 2, nothing. Okay? So that was roughly how you used your activity series. The further up on the activity series, the more reactive it was, the more willing it was to become an ion. And we kind of left it at that. Okay? What type of reaction is occurring when we look at our activity series? It's zinc going to zinc ion. How does it do that?
Oxidation.
Has to lose electrons, which is oxidation. So the activity series is just a way to roughly approximate different oxidation potentials, how likely something is to oxidize. Okay? When we move into 152 with thermochemistry, what we're going to end up looking at is standard reduction potentials. I have no idea why they decided to swap on it. I'm going to guess it's some kind of convention. So the standard way to report all of these things is going to be in a reduction potential. So what we do is take a look at furthest or highest up on that chart, in this case fluorine, going to fluoride. To do that, it would need to gain electrons, so it would need to reduce. Okay? The higher it is on that chart, the more likely it is to occur, just like our oxidation potentials. The lower on this chart, the less likely it is to occur. What's the it occurring in this case? This is a standard reduction potential. The higher on this chart, the more likely to reduce. Okay? One of the issues that we'll find with this is higher versus lower. Okay, why did we decide to put fluorine up top? Okay, why did we decide fluorine was higher or should be higher than lithium? Kind of an arbitrary determination. So what we end up having to do is come up with a sequence of numbers to represent these. Okay? So when we go through and look at our reduction potentials, make sure that you evaluate these carefully. Shucks, I was hoping I had some numbers on this. We can go through and look at our reduced, our oxidized, strongest oxidizing agent, and strongest reducing agent. identifying all of those pieces off of our chart. Okay, this is what I was looking for. How do we decide what's highest and lowest? Someone went through and determined what's known as your potential. They put a numerical value to the potential of each of these reactions occurring. So when we take a look at fluorine, it's the highest because, what's that number? It's the highest potential. Okay? So it just happens that we decided to put highest with highest because that kind of makes sense. Okay? Doesn't have to show up that way, but that's one of the ways we can represent it. So when we go through and look at our reduction potentials, what we're looking at is a positive potential being a good thing. Okay? The more positive the potential is, the more likely that that reaction is to occur. So when we look at fluorine going to fluoride, how likely is it for that reaction to occur? To go from fluorine, F2, to fluoride, F-. That's a good reaction. Why is that a good reaction? We have a high positive potential for that. If we take a look at lithium ion going to lithium metal, is that a likely reaction? No, because what we'd be looking at is the reaction occurring here. Lithium ion going to lithium, that has a negative potential. What happens if we swap that? Now instead of it being lithium ion, we make it lithium metal. Lithium metal going to lithium ion. What type of reaction is that? Oxidation. Is that likely to occur? Okay, yes. Now the question is why? What's that? So you came up with a natural next step on this, which is sometimes fatal, but this time works. What happens when we flop the reaction? What happens to the cell potential? Changes its sign. Okay? So if we look at the likelihood for lithium metal going to lithium ion, is that a good reaction? Lithium metal going to lithium ion? Yes, because what happens to our potential? Becomes positive 3.05. Okay? So you will be using the reduction potentials to determine if a reaction is likely to occur or not. So what we're trying to do is look at how those individual reactions add and subtract to give us the potential for that reaction. Yeah, Chase. No, that's fine.
If you swap, like you're swapping the last one, the metal lithium to the ion, would the potential be positive 3.05?
Yep.
Oh.
Let's take a quick example with what we've been looking at. We said zinc. Please say they're both up there. Yes. Zinc going to zinc ion and copper. Copper ion going to copper metal. What is the potential for zinc going to zinc ion? Zinc going to zinc ion. That is positive 0.76. Why is it positive? We've reversed the reaction. How about copper metal going to copper, or sorry, copper ion going to copper metal? Positive 0.34. When we add the reactions, what can we do with our potentials? We can add them as well. What's our potential for this reaction? Positive or negative? Positive. What does that mean? This reaction will occur. What happens if we swapped it? We go with the reaction that we said didn't occur. In that case, what do we have? We had copper metal going to copper ion and zinc ion going to zinc metal, right? What are our potentials for each of these reactions? Copper to copper metal is negative 0.34. How do you know it's negative? We reverse the reaction. Take a look at the zinc. What happens with the zinc? Negative 0.76. When we add our two reactions up, what's the potential? Negative. Is that likely to occur? No. We're pushing into that negative territory. Negative, as far as potentials go, is bad. So what happens? No reaction occurs in this case, which is exactly what we saw. Okay, first Seth, and then you.
So in the homework, there's a question using gold and zinc.
Yes.
And the way when you separate the cathode from the anode,
Mhm.
you would think you'd want to switch it the way it's set up. So I did it for the problem, you got it wrong. When do you know when to switch it from a negative to positive?
When you're wanting a positive cell potential is going to be the first thing. Okay? So if we ask for the cell potential for an individual reaction, you have to do whatever that reaction says, period. If I say I want the cell potential, the positive cell potential for the reaction involving these two ions, or these two species, you have to set it up such that you get a positive cell potential. So it's going to depend on what the question is asked. So I'd have to look a little bit closer at that. You said it was Connect? Sapling homework? I'd have to look a little bit closer at that to see what they were looking at. Yeah? Nope. I think I've got this in an equation format here in a second. So to get our water wheel to function, we have to flow from high potential to low potential. So we're looking for that positive value. Yeah, we'll go ahead and almost finish this. So when we're looking at the flow of our electrons, we're looking at this electric flow. We'll represent that flow as a charge, or sorry, an energy flow per charge of our electrons. Okay? Our energy is in units of joules, so that one's fairly standard. Our charge on an electron is known as a coulomb. That's where we get our joules per coulomb. Because nobody likes fractions, what we end up doing is coming up with a new unit. That new unit is volts. So when we represent our potentials, those potentials are in units of volts. Okay, and we're referring to the electric flow. Shoot. Okay, I thought I had the equation up here. Okay, that's the equation that we just looked at. We'll come back to that tomorrow. So our cell potential is equal to the oxidation cell potential plus our reduction cell potential. It is a slightly different format than you'll see in your textbook, but it's the one that I prefer. You'll get the same answer either way.